start section 3.6, modeling with exponential and logarithmic equations. So this is kind of a catch-all. We're going to kind of clean up some things, including literal equations and some application problems, some story problems that use, as the title indicates, exponential equations and logarithmic equations, which we were just practicing solving in the previous sections. Do you remember a literal equation typically means an equation that has lots of letters in it, lots of variables. And in this particular example that I have here, I only have three variables. I have capital T, lowercase letter t, and k, lowercase letter k, and that's the one we're solving for. So you may remember from before, to solve a literal equation, we solve and isolate the variable in question, which is k. So I have to get k. Notice where it's at. It's up in the exponent, so that's going to be a little bit of a challenge, but we can get there. First things first, we're going to try to isolate the term that, I shouldn't say the term, but the factor that has the variable in the exponent that we're solving for. So I'm going to try to get this all by itself. To do that, I'm going to subtract 78 from both sides. So that'll cancel out. I can't do much over here on the left because these are not like terms. And then I'm going to divide both sides by 272. Kind of cheap out because I don't have a lot of space. And combined steps here, we really shouldn't do that. T minus 78 all over 272 is equal to e to the opposite of kt. Now, to get the exponent out where I can work with it, I notice that it's a base e exponential expression. I will take the natural log of both sides, and I can do that because these are equal and this is a positive amount, and you can take the natural log of a positive amount. So I'm going to take the natural log of the expression t minus 78 all over 272, and I'm going to take the natural log of e to the opposite of k over t. This is where it comes into play, where we can use that property that allows us, it's one of the laws of logarithms, that allows us to bring the power out in front as a constant. So I'm going to write the natural log of t minus 78 all over 272 is equal to the opposite of kt. Now I'm going to come up here, I'm going to solve for k here, so I'm going to divide through by the opposite of t. So I'm going to take the natural log of the quantity t minus 78 all over 272, and I'm going to divide that by the opposite of k, and of course I'm going to do the same thing with the other side, divide by the opposite of k, and I get, opposite of k, opposite of t. I'm solving for k, let's try that again. I'm going to divide by the opposite of t, almost messed that one up, and that's going to give me a mess here over here. This is going to cancel the opposites, I get k equals. Now, I'm going to bring all this over here, but there's all sorts of things I can do here. Because I have a logarithm in here, and I have a quotient, so I can use the quotient rule. What I'm going to first, though, do is I'm going to bring the negative out in front here. I'm going to write this as the opposite of the natural log of t minus 78 all over 272 all over t. Now, there's nothing really wrong with this answer. It can be rewritten, and you have to check, because if this was a problem you want to check the answer in the back, you might have something that looks quite a bit different than this one in the back because of the logarithm. I mean, I could bring this negative, which is like a -1, up here as a exponent, and that would give me k is equal to the natural log of t minus 78 all over 272 to the -1 all over t. And of course that means I can rewrite this as the natural log of 272 all over t minus 78 to the positive first power over t. I could rewrite this as 1 over t, the quantity, the natural log of 272 minus the natural log of t minus 78. There's a lot of different things that I can do here because of the logarithm, so be sure to check your answers carefully. When you get into differential equations, it'll take you 2 minutes to solve the differential equation, and it'll take you 5 minutes to match the answer in the back of the book. This is one of those kind of problems that's going to be kind of messy that way. This one's got a little bit to it as well because of the logarithm, but I am solving for t, so if s equals 90 minus 20, a natural log of quantity t plus 1, solving for t here. So what I'm going to do is I'm going to try to get this by itself this time. And to do that, I'm going to subtract 90 from both sides. I don't have very much space, so I'm going to kind of just subtract 90 off of this. not necessarily the best way to write it, but I want to squeeze it in here. And then I'm going to divide both sides by negative 20. Now, if I divide by negative 20, I'm really not crazy about a negative denominator here. So it's as if I could bring that negative up to the top, like a negative 1 multiplying top and bottom by negative 1. This becomes 90 minus s, I multiply by negative 1, all over 20, equals the natural log of t plus 1. Now, to get rid of a natural log, I either have to try to match the expressions, which I can't, or I take both of these and I raise them as exponents to the e power. So I have e to the 90 minus s over 20 is equal to e to the natural log of the quantity t plus 1. That's quite a trick there. And then I am going to use my property of logarithms or exponential expressions and logarithms here, and I'm going to write this as when you have base e, you just get the expression t plus 1. I'm going to go ahead and write t plus 1 on the left, and then over here, what a mess this guy's looking at. And then I'm going to subtract 1 from both sides. I'll put parentheses around there. Minus 1. And this guy right here is my answer. Now there's probably a way you could rewrite this as well. I definitely could do something with this expression here, but I don't think it has quite as many options as the one from before, which I did not outline. Sorry about that. Okay, so you're going to have to practice a little bit with these literal equations. They're a little bit messier, about as messy as I think you will see with the literal equations. Now, I'm going to come back over here and show something that has to do with what we call exponential growth and exponential decay. We've mentioned it in the past based on the graphs, going increasing for exponential functions, increasing from left to right, decreasing from left to right. Let y be a variable. Let y be a variable changing exponentially with respect to t, and we like to use t because of time. And let y sub 0 represent the initial value of y when t is 0, the initial amount. Then, for the constant k, if k is positive, then this expression, y equals y sub 0 e to the k over t, this equation, not expression, is a model for exponential growth. K is positive, growth. If k is less than 0, then y equals y sub 0 e to the k t power is a model for exponential decay. Alright, so that kind of makes sense. Positive growth, negative decay. Alright, suppose that $10,000 is invested, and at the end of 5 years, the value of the account is $13,771.28. Use this model, which we've looked at before, A equals P to the RT power, to determine the average rate of return R. So we're solving for R here under the continuous compounding. Now when we had this before, we were just plugging in some values and solving it. We weren't solving for anything in the exponent. Now we are. So to solve this, first I'm going to plug in what I know, and then I'm going to hopefully have everything figured out to solve for for whatever variable remains. Now, this is the initial investment, $10,000. This is P. This is the time here. T is equal to 5. And this is your amount here that you're going to have in the account, $13,771.28. I'm going to plug all that in. I have $13,771.28 is equal to 10,000. E, of course, E is a number. Not a variable, to the r, which we do not know, but to the t, which is the fifth power. Just like I did back here, I'm going to solve for the variable r, in this case that's in the exponent. It's k last time. Divide both sides by 10,000. Okay, when I divide this by 10,000, it's like sliding the decimal point 1, 2, 3, 4 places to the left. I get 1.377128 equals e to the 5r. I'm going to take the natural log of both so that I can do what's necessary to get at the exponent there, which has my variable. The right side, natural log of e to the 5r is 5r equals the natural log of 1.377128. I'm going to divide both sides by 5. and I'm going to get r is equal to, now when you take the natural log of that number and you divide it by 5, you'll get 0.064. And that is the rate of return written as a decimal. We're going to write our answer with a percent. So slide the decimal 2 places. So the average rate of return is 6.4%. And that's the answer to that one. Now we have other applications that we're going to look at, but this guy isn't going to go too far away. Now in calculus though, we actually kind of derive this formula here from a differential equation. And I know that doesn't maybe make a whole lot of sense now, but we're going to end up with stuff that looks a little bit like, instead of a p, we're going to use c for a constant, e to the kt. You can see how similar it is. Different variable here, k, and different variable here, although we do have the k up in this one. So this is something you're going to see again in calculus, so it'd be best to remember it.